So, so I'm no trouble covering everything, but that means it gives us some time now to talk about
Wednesday.
homework 3. And let's see. Okay, Ashley's online, so we can get her Skype in momentarily. So let's talk about. Whoa. Okay. Yeah, class started a little late. So, who has questions about any problem on homework 3? I have time to get pretty detailed.
Okay, so on number 3, you said to, let me pull these for a minute.
Here.
You said to like, do you have it printed out?
I thought I did, but
To go in MATLAB and kind of like go through the iterations.
Yeah, but it's a good idea to actually, like, if you take the matrix from part C, and any vector chosen for B, and actually just try out the iteration and see how it behaves, because for general B, the iteration will fail.
Wait, let me make sure that we're talking about the same thing.
Okay.
Okay. So we're talking about number 3. Yep.
Yes.
Okay. Okay, so you said that for a general B, it will fail?
Yes, the iteration won't converge.
Okay. But then we should see something.
Yeah, so the behavior is observed, because the idea is, actually, it may not be too informative if you look at the X that it's putting out with each iteration. Instead, look at the difference between xk plus 1 and xk, the difference between successive iterations, because for a conversion iteration, you should just see that vector go to 0.
Okay.
And you'll find that it won't this time, but see what it is doing.
Okay.
Also, for this particular matrix, okay, so this is problem 3C. Your matrix is it's called a circulant matrix. So it has 2's down the diagonal, and then we have -1's down the super diagonal. But what happens is, -1's going down, and then it goes off the edge, and it circles back around to have another -1 here. And then we have -1's on the subdiagonal, and when it goes off the edge here, it comes back up here. So that's where the term circulant comes from. And this is a singular matrix. And an observation to make about this matrix is that all of the row sums, so if you sum the entries in any row, all the row sums are 0. So from that, you can draw a conclusion about what is the null space. So, so it turns out that the null space is this is one-dimensional null space in this case. It's quite easy to describe. So if you figure that out beforehand and then try the iteration and see how it's behaving, this will give you an insight as to what to do to fix this iteration for a more general symmetric matrix. Because for a general symmetric matrix, you're not going to be able to figure out the null space as easily. It may be multidimensional. So is this something you've already tried, like with Gauss-Seidel or something? Or?
Yeah, but I was just looking at like the x's.
Oh, okay, those are going to diverge.
Yeah.
So.
Yeah. So I was wondering, I wasn't seeing anything.
Oh yeah, you're not going to see. It's going to be hard to see anything interesting from that. But yeah,
okay, look at the difference in
yes.
iterations.
Yeah, let's see. If you're trying iteration out, have it print out the difference difference between the new iterate and the previous iterate. And since it won't go to 0 in this case, see what it does do. That sounds redundant. What it does do.
And now the new iterate and
The new iterate and the previous iterate. So the difference between xk plus 1 and xk. Since you would normally want to have to go to 0. No. I said no, I should not answer that. No.
So that's what it does, okay.
That's not entirely correct. But, okay. Now, so a couple other comments I want to make related to this part. All right. So one thing to keep in mind is so the null space of A, in the case where A is actually, I won't bring a symmetry into it yet. The null space of A, so that is spanned by all eigenvectors, and when I say eigenvectors, I really mean, I can't write, all linearly independent eigenvectors with the eigenvalue being 0. Because what do you have when you have a null space? You have A times x equals 0, where x is a non-zero vector. So that's the same as saying A times x is equal to 0 times x. So we're talking about eigenvectors that have an eigenvalue of 0. And in part A of this problem, you're relating all of these eigenvectors to certain to the eigensystem of M inverse n. Now, because A equals A transpose, you know that the null space of A is orthogonal to the range of A. Normally, it's orthogonal to the range of a transpose. As a result, here's what you can do. You can take any vector x in Rn and decompose it in a unique way. So x is equal to some vector x of n plus another vector which we'll call x of r. And this is in the null space of A, and this other vector is in the range of A. Now, so if you think about the difference between consecutive iterates, as you go from iteration to iteration, that is being multiplied by M inverse n. And if M inverse n had eigenvalues that are less than 1 in absolute value, that difference between iterations would go to 0. But if there's not, but in part A, you're supposed to show that there's at least one eigenvalue that has that is equal to 1. So, okay. So to get an idea of what's happening from iteration to iteration. Okay. So, given a sequence of vectors, I'll call them like y0 equals, it doesn't really matter, some non-zero vector. And then subsequent vectors in a sequence are obtained by multiplying by M inverse n. So if a vector is a sequence, or just some vector randomly chosen times powers of m inverse n. Okay. Now, yk can also be decomposed uniquely, and this is a consequence of part A. So decomposition into two vectors, and this belongs to the span of eigenvectors of m inverse n, where the eigenvalue is equal to 1. So in part A, you prove that such eigenvectors exist. And y2 is in the span of all the other eigenvectors. M inverse n, where the eigenvalue is less than 1 in absolute value, assuming that the iteration would converge if it weren't for this singularity. So what happens is yk is equal to m inverse n to the kth power times this decomposition applied to y0, and then m inverse n to the k power times this portion of the other portion of y0. Now, this part corresponds to the eigenvalues that are less than 1 in absolute value. So as k goes to infinity, this part's going to go to 0. Okay, that's what you want to have happen in general. What's going to happen to this part? This part, as k goes to infinity. What? Yeah, it's going to stay the same because it's always going to be multiplied by the eigenvalue 1. So in fact, you can just get rid of this. It persists. So if you try out the iteration and look at this difference of iterates, you'll see something like this happening. And the thing is, if you know that there's this part of your vector b, that you don't want to be there because it's going to cause the iteration to not converge, what can you do about it? And this is why you're changing a problem from ax equals b to ax equals b tilde, where b tilde needs to be in a range of a, just so you'll have a solution. Because if it's not, this is not going to have a solution anyway. Your iteration would never be able to converge to a solution that simply isn't there. But this you can make your iteration converge to. So see what you can do to try to. And again, I recommend trying the iteration out, seeing what happens. As far as knowing that you have a decomposition like this, where these vectors, y1, y2, belong to orthogonal subspaces. So the way that you can separate them is with something I talked about early on in the semester that's called projections.